Hello students. First of all, thank you for watching my videos and supporting me enormously on YouTube and on my channel. So if you'd like this video, please like, share and comment. If you have any questions similar to this and if you want me to answer, please share with me those questions in the comment section. I'll try my best to answer those in another videos. Okay, one of my student from Florida has shared with me this particular question. It says Coumarin and its derivatives exhibit a broad array of industrial applications, including but not limited to cosmetics, food, preservatives, and fluorescent laser dyes. Some derivatives of coumarin, such as warfarin, exhibit an antimicrobial antithrombic activity and are currently used in blood as a blood thinners. So the question is asked here, identify how you might use the IR-spectroscopy to monitor the following reaction, in which compound 1 is converted into a derivative of coumarin, compound 2. Okay, so let's first understand how exactly this reaction is happening and what are the changes happening there. If you look at this particular reaction, the compound 1 contains a phenolic OH group and an aldehyde and the benzene ring, of course, and the tertiary amino group or aniline group as well. In a compound 2, as a product, you have a cyclic ester, a conjugated ester, so to say, a conjugated ketone, and rest everything remains the same. So in an IR spectroscopy, we generally describe or we generally find the respective functional groups with a certain specific frequencies or the vibrational or different kinds of bond frequencies. So compound 1 contains the phenolic OH group, so that's why compound 1 is expected to be. Let's first list down all the possible IR signals in the compound 1 and then compare that with the compound 2, and then we can define or decide how you can monitor this particular reaction. So compound 1 contains phenolic OH, which can have a broad peak around 3200 to 3500. Of course, not limited to this, but somewhere around 32 to 3500, a broad signal. Broad and strong as well. These are the characteristics of a phenolic OH. Of course, it's not only phenolic OH, alcoholic OH will also have a similar kind of frequencies. Go to aldehyde. Aldehyde, it's generally it comes somewhere around 1700 to 1720. However, here that aldehyde group is in conjugation with a phenolic, the phenyl ring or aromatic double bonds. So that's why the desired frequency of that aldehyde group will be decreased a little bit. So it will come somewhere around the carbonyl vibrational frequency, a stretching frequency, so to say. Broad, strong, and this is related to stretching. So aldehyde C double bond O stretching frequency. So C double bond O stretch, and that will come somewhere around 1700. It is expected to be somewhere around 1700. It could be less than 1700 as well. In fact, I'll put a range around 1680 to 1700 centimeters. That's for an aldehyde. Another aldehyde functional group has a specific frequency CH bond there, sp2 hybridized carbon attached to hydrogen, so CH bond, and that is aldehyde CH stretching. This stretching comes somewhere around 2750 to 2800 or 2850. It depends. So this would be a characteristic aldehyde frequencies present in the IR spectrum of compound 1. On the other hand, compound 2 does not contain an aldehyde and does not contain a phenol as well. So definitely compound 2 will have different signals as compared to the earlier compound 1, the starting material. So aldehyde is converted into a ketone maybe, and or different functional groups maybe, and the OH, phenolic OH, is now no more there, and it is ester instead of that. So these are the main changes happening in a functional group. So we'll monitor specifically the IR frequencies changing in those functional groups. So compound 2 contains C double bond O, that is in conjugation with C double bond C. So conjugated C double bond O, a ketone carbonyl. So ketone carbonyl is expected somewhere around 1700 or somewhere around 1700, so to say. So let's make 10. This would be ketone stretching. This would be 1700 centimeter inverse. Then you also have an conjugated ester. General ester would come somewhere around 1745, but due to conjugation it is lowered, and so that will come something around 1700 as well. So conjugated C double bond O of an ester. This is again a stretching frequency, and that leads to 1680 to 1700. Okay. This I'll put a range, by the way, 1680 to 1700. This would be definitely greater than 1700 IR frequency. So we can write about the change in frequencies or monitoring the reaction progress by monitoring the change in frequencies. The phenolic OH frequency or that particular peak will vanish because that's not present in the product. Aldehyde, C double bond O and a CH stretching frequencies, the peak with respect to those will also disappear in compound 2. Whereas conjugated ketone, the peak associated with that, and ester, conjugated ester peak will also appear in the compound 2. So these particular peaks will disappear, and these particular peaks will appear in the reaction, and you can easily monitor that particular reaction by monitoring this disappearance and this appearance signals or peaks in the IR spectrum. Okay, and so we can stop here. So if you have any questions similar to this, please share with me in the comment section. I'll try my best to answer those. Thank you for watching my video, and please like, subscribe, and share the content to your friends and other students, those who are in need of this kind of a help. Thank you.